So last time we saw this problem, we finished it up. So now, in that example, we could not have solved that one using Newton's laws. And that's because the acceleration was not constant. With Newton's laws, we always had constant acceleration. That problem did not have constant acceleration. Therefore, we could not have used Newton's laws. But with conservation of energy, it was actually a really easy problem. So once you get the hang of conservation of energy, you'd think that was actually a really easy problem. I guess if you don't know conservation of energy very well, then you probably think that's not a really easy problem. But anyway, this one, we have the thermal energy of a trip down a slide. So we're at rest at the top of a playground slide. The main part of the slide is 5 meters long, tipped at a 30-degree angle. Start sliding, moving down the tipped section, and then the slide levels out so that we leave the slide at 2 meters per second, moving horizontally. The mass is 24 kilograms. How much thermal energy is deposited in your trousers and in the slide? Trousers is a great word. So what do we do?
Draw a picture.
Okay, we'll draw a picture.
Very simple picture.
A simple picture. So we have the elevation of the slide, the ground, and the slide. That's pretty simple. Probably do the slide too long, but it doesn't matter. So we have the kid up here sliding down the slide. He's probably happy. All right. What do we know?
The slide itself is 5 meters long.
Okay.
And it's tipped at a 30-degree angle. So does that mean like from the horizontal?
30-degree angle, yep. Okay, what else we know?
Let's see. So his final velocity is 2 meters per second.
He leaves at 2 meters per second, yep. So V final would be 2.0 meters per second down here at the bottom. What else do we know?
So his velocity initial is going to be 0.
By the way, down here at the bottom, here he is. And still smiling. There we go.
Y initial. Or Y final 0.
Okay, Y final. 0 meters.
And then we can do sine.
Mass is 30 or 24.
Sine. Why are we doing sine?
To find Y initial.
Okay, so for Y initial, sine 30 degrees would equal this Y distance right here over 5 meters. Yep, opposite over hypotenuse. So what do we get? Actually, sine 30 degrees is what? You unit circle people?
Oh, that's Gabe. He remembers all that.
Square root 3 over 2.
No.
Wait.
I thought it was just 1/2.
It's 1/2. Yeah, it's 1/2.
So 1/2 of 5.
1/2 of 5.
2.5.
2.5 meters up here. So Y initial is 2.5 meters. And what else do we know up there?
Velocity initial.
Velocity initial is 0 meters per second. Okay. Wow. Meters per second. Okay. And what else do we know?
Mass 24.
Okay. Anything else?
Nope.
Okay. So what do we do?
Our big equation, the work.
Work energy equation. So we have, let me change color. We have change, so KF plus potential F plus delta thermal equals K initial plus potential initial plus work.
We can eliminate
What are we eliminating?
work. So we can make this a close system.
Can we eliminate work?
Yeah.
Yeah, we're not putting any energy in. So work is gone. What else can we get rid of?
K initial.
K initial, the kid's not moving.
And then
Potential
potential final.
Potential final, we're all the way down on the ground.
Yep, that's what we can get rid
That
of.
it?
Because we have to go for thermal.
Yeah, we're talking about thermal here, so we got to leave thermal in. And yeah, that's it. Okay, now what?
So 1/2, we could move the kinetic final.
Kinetic final to the other side. Okay, so we have delta energy thermal, which always stays delta energy thermal equals
Potential initial minus kinetic final.
right. Okay, so now what should we do?
Write the energy equations in the right places.
Yeah, switch them over. So this will be, what would I be?
Mass times gravity times Y initial.
Y initial. Okay, and then minus, what's KF going to be?
1/2 mass velocity final squared.
Velocity final squared. Okay. Now, we know M, G, Y initial, we already calculated. 1/2, we know M, velocity final, we were given. We know everything.
Yeah,
So we can solve. So delta thermal. I'm going to factor out the M. So that was 24 kilograms. Okay, 9.8. Y initial, what was it? 2.5 meters?
Yep.
Minus 1/2. I factored out the M. And then V final, 2. Don't forget that squared. Two squared is 4 times 1/2 is 2. We got 9.8 is around 10. So that'll be around 25. 25 minus 2, 23. 24 times 23.
I got 540.
Yeah. 540.
So what's the units then for this?
So what's units? That's a good question. So we have kilograms times meters per second squared would be newtons
And then
times meters. Newtons times meters is joules. As it should be, because we're talking about energy. So we're good. So the energies present in the isolated system can transform from one kind to another, as we saw earlier in the chapter. But the total energy is conserved. All the units of all types of energy are the joule, just like we just saw. The kinetic energy is the energy of motion, so K equals 1/2 mv squared. The gravitational potential energy is stored energy associated with the object's height above the ground, or whatever the surface is where we would consider it starting or finishing if it became a free fall. So we have G as free fall acceleration and the height above the reference level. So the table, the floor, the earth, whatever it might be. The elastic potential energy, so with the springs, this time we have 1/2 kx squared, and we saw that one being used as well in this section. We have work, the transfer of energy into or out of the system by an external force. So we didn't see any examples with this one because we were conserving energy. This is outside of the system. So work into or out of the system, positive or negative. And then force has to be parallel to the displacement. So as long as we're moving in a certain direction, the force has to be parallel to that. Anything that's perpendicular to that does not count. And then before and after work and energy equation captures the law of conservation of energy. So we have kinetic final, potential final, delta thermal. Remember, we can never change that one. It's not initial and final. It's just always delta. And then equals kinetic initial, potential initial, plus work. So there you go. That's everything that we talked about. And we did examples with all of that, except for work in this section, because in this section we were talking about conservation of instead of adding and subtracting. So finally, at the water park, Katie slides down each of the frictionless slides shown. At the top, she's given a push, so she has the same initial speed each time. At the bottom of which slide is she moving the fastest?
D,
D? Why?
because the heights are all the same.
The heights are all the same.
She finishes at the same height. She starts with the same speed.
Uh-huh. Starts with the same speed, finishes at the same level each time, and it doesn't matter how she drops.
She's moving the same.
So her speed is the same at the bottom of all three slides. She might get to the bottom faster, but her speed is the same in all three cases. Okay? This doesn't ask about time, this asks about speed. So the answer is D. Good.